Thank you. Alex was sent by his employer to Jordan, so he's enjoying the Middle East. And it's sunny. If there's nothing about Binghamton that's true, it's sunny. It is the cloudiest city east of the Rockies. But I'm pleased to be here today to talk about the efforts at Binghamton and also the program that Alex is managing. The long-term goals are to increase the number of in-orbit spacecraft, you heard about that earlier, leverage current design objects, including AMSAT and others, creatively approach launch opportunities. You heard that also. The idea is to have something that can be put together relatively quickly and be available when launch opportunities result. Increase educational outreach. Our university is one example. Maintain an experimental edge. We'll talk about some new technology today. And finally, to provide a stable technical program office. One of Alex's priorities is to engage university participation, and he asked us at Binghamton to become involved, and we're delighted. We had a very strong team of students this year of electrical, computer, and mechanical engineers involved in this. Also, there are a lot of talented volunteers that we're pleased to work with, and the principal idea is to maintain an evolutionary design approach and use those kinds of principles to continue to improve, but not necessarily redesign every project over and over from scratch. The NextGen program that Alex manages is a partnership between AMSAT universities and industries. The industry here is IBM, that's Alex's employer, to build the next generation of amateur radio communication satellites. I have to say a word about Binghamton. The SUNY system has 64 campuses. Three of the university campuses have engineering programs: Stony Brook, Buffalo, and Binghamton. Binghamton is a little larger than Stony Brook, a little smaller than Buffalo in terms of engineering enrollments. We're the most selective undergraduate program in the 64 SUNY campuses. And as I said, IBM is involved through Alex on their Heritage Corridor Center. This program was announced in October '09, and Alex is the program manager. I'm an electrical and computer engineering faculty member from Binghamton. The evolutionary design uses current assets, so we'll also insert new technologies to improve capabilities, provide launch-ready modules. So one of the outcomes of our work at Binghamton is to have modules that can be used at no or low cost by others. We're going to provide AMSAT a cube launch-on availability capability, and we hope that every one of these programs will involve an Oscar payload as well. Another part of this is to encourage the next generation of young people, and we've already begun the conversion of a number of our talented students to become hams. A number of the students engaged are staying on next year as graduate students and will remain involved. It's important to offer complete assemblies at low or no cost to other Cubesat universities so they can focus on payload and not upon some of the infrastructure needed. AMSAT management of spacecraft during the primary mission is a primary component, and when it's over, the spacecraft will be turned over to AMSAT for a secondary mission, an Oscar in every Cubesat. The goals this past year have been to leverage the ARISAT-1 technology into a much smaller 3U Cubesat frame, and there's at the AMSAT exhibit there's an example of the work of the students. A little sketch is shown here. It has four deployable panels. You can certainly pick it up and see how it works. The working models have spring-loaded. They're made to work once. so it can be packed in a compact size. And another key effort was to increase the reliability and longevity of the spacecraft. The reason for the deployable panels is to have a much larger surface area to produce larger powers that may be necessary for some experiments. This year we met the goal set out at the last year's symposium. We've begun to leverage the technologies to fit within a 3U CubeSat frame. Just to remind you, that's 10 centimeters by 10 centimeters by roughly 10 centimeters times 3. So it's a long rectangle. We're learning from ARISAT 1 and prior spacecraft to apply. And there is, as I said, a display model of that device out there for you. We're also looking at improving the power system unit, and we have worked this year to use pseudo capacitors, which are related to supercapacitors, as a way to replace the batteries on spacecraft. And out there on the exhibit are some of the supercapacitors as well. We've assumed for a worst-case orbit that this satellite that we have will provide during an eclipse at least 7.5 watts of power. We intend to continue to work on this. In fact, we're working over on this project this summer with some of the grad students who want to push ahead. Shown in the yellow are the areas we focused on: the solar panel systems, the energy storage systems. I'll say something about it in terms of pseudocapacitors, the power supply unit, and the interconnect board, which we've begun to work on. The other systems you've heard about as well. We'll try to incorporate into a geometry, many of which already fit into the 3U CubeSat. In terms of the power portion of the project that we worked on, there were a number of possibilities. Certainly one was to use lithium-ion batteries, which have good energy and power densities, but a relatively low lifetime. Batteries are notorious for the not having very many cycles of charge and discharges. Another possibility is what's called a supercapacitor, sometimes called the electrical double-layer capacitor, which has a high energy density, lower power densities, and a nearly infinite lifetime. These things can be charged and discharged rapidly, millions of times. Because of space and weight constraints, we picked a variation on this called the pseudocapacitor, which has some features of both supercapacitors: very high capacitance with some battery-like characteristics, and it has a high lifetime, not perhaps as long as supercapacitors, which will last many millions, but on the order of a few 100,000 to 500,000 plus charges before it begins to lose some of its capacity. There is a U.S. manufacturer of these devices. It's Ioxys. They're located in Oneonta, New York, and we've used theirs. There are examples out there. These are smaller than a C-size battery. They look like a AA perhaps on that slide, a little larger than that. They're 220 farads. When I was a student, there were legends about how big a 1 farad capacitor could be. But nowadays, you can hold a bunch of these things in your hands on the order of 1,000 farads plus with no difficulty whatsoever. There are non-U.S. manufacturers, but we decided to use a U.S. manufacturer. We like them because they did custom capacitors for the Department of Defense, and they have a reputation for high reliability and telling more or less the truth about how their devices perform. There's a slight lifetime decrease, but that can be minimized by controlling the depth of discharge of the supercapacitors. We tested them in a number of ways. One is vacuum test. These are not designed by the manufacturer to survive long times in vacuums, but we found that we could seal them at the ends with Torseal epoxy sealant. It was put in a vacuum chamber, left for a long period of time, and 10 to the -5 torr, and it worked fine. We also thermally cycled the capacitors from about room temperature to 65 Celsius for a number of hours, and again there was no observable degradation. We're unable, with the facilities we had available, to do a freeze test of these things. We do have shake and bake facilities as well, but we haven't done those yet on these capacitors. Ioxis rates the capacitors down to -20 Celsius. The voltage across these capacitors is a maximum of 2.3 volts. So to get the working voltages we need to assemble them in strings, series and parallel strings. The concept design we have involves 42 of these devices. You need some resistors to balance them because if you try to charge capacitors in series, there's problems with them. But with this configuration, we have 256 farads that can operate up to 13.8 volts. And you'll see the number of joules that can be stored. In contrast to battery-powered devices, where the voltage across the battery remains relatively constant, the voltage across the supercapacitor or pseudocapacitor decreases as it's charged. So it's necessary to use somewhat different conversions in order to provide the power for the system. So in the prototype you have out there, you'll see it produces 8 volts and 5 volts. The supercapacitor bank or pseudocapacitor bank is allowed to discharge down to 6 volts. So we need a SEPIC circuit to raise the voltage back up. And they work perfectly. We're working this summer on the MPPT part of it, which is a little different from what you need from voltage sources. And we're testing it with solar panels, but not with the solar panels normally used in space. We're using terrestrial solar panels to do the charging and discharging. Over the next year, we're going to run relatively long cycles, as long as we can, up to a year of charge and discharge of these supercapacitors to look for degradation after a number of cycles of shake and bake and so on. It says at the bottom, Alex put it there, a supercapacitor bank is only drawn to 50% to maximize the lifetime. Actually, that's 56% of the voltage, but it's actually we use 3/4 of the stored energy because the voltage across the capacitor goes as V squared. So there's a lot of energy stored. And the estimate based on the manufacturer's specifications is 17+ years before you lose 30% of the capacity of the supercapacitors. In terms of the mechanical overview, the goal is to reduce the AMSAT volume by a factor of 20 to fit it into the single 3U CubeSat, and you see a little sketch of what the students have out there on display. And the emphasis was placed on collecting optimum solar energy as well through a panel deployment. Basically, there are 4 deployable panels on the sides. They're at 45 degrees, as you can see, in a sense, so that they don't shade one another. And under optimum conditions, they can get 33 watts produced. Under worst case orientation, 16.5 watts. If you don't need all that energy, then you can use fewer deployable panels, or you can reduce the number of supercapacitors as well. deployment was designed so it could fit into the standard package. They're constrained by polyethylene line. The lines are melted by resistors, and torsion springs deploy the panels into the final flight configuration. So the students did a complete, careful mechanical design and lots of mechanical testing. So you just heat up a resistor, and the line pops, allowing the spring to turn. And there's a locking mechanism which will hold the panels in place once they're out there. So it works well. Recommendations are to continue to build and modify subsystems, including the attitude determination and control, spacecraft command and control, power generation and distribution. We still have the MPPT to finish this summer. Work in the software-defined radio. We have to do more studies on thermal management on this system, and then look at the integration as well of everything that has to fit in along with the power, mass, volume, and thermal budgets. So these are things we'd like students to continue to work on over the next year. That's thanks to me. I'm actually very happy to be here, and the person who's driven this intellectually and energetically is Alex, and here's his email, and he'd be glad to hear from you, especially if he's in Jordan, which is not the most exciting place to be. Maybe Dayton is. Thank you.